we have started lecture series on CSIR NET SET Gate and other competitive exam. Already I uploaded plenty of the videos from these exams. If you wanted to see this video, you may check it into my playlist. So in my today's video, I'm gonna explain to you all one of the question. It is from CSIR NET previous year question paper. All are the question which is from the latest question paper. Okay. Now let's get started with today's question. First of all, I'm gonna explain to you all the question, and then we'll move for the detailed understanding of our solution. Question we have given which of the following series convergent. Okay, which of the following series function or series given which is convergent. Okay, so first series it says that if we take a which is equal to a, first option, if first series is given n is equal to 1 to infinity n square into 2 raised to minus n, so we have to figure it out, is it convergent or divergent. Second option it says that we have second series n is equal to 1 to infinity n raised to minus 2 into 2 raised to n. Third option it says that n is equal to 2 to infinity summation 1 upon n log n. Okay, so and fourth option it says that n is equal to 1 to infinity 1 upon n into log of 1 plus 1 by n. Okay, so we have to figure it out which one of the series which is correct over here. Okay, so because of the question it is from the paper third, 4.75 marks, so that means two or more than two options are correct. Okay, so we have to check each and every option very carefully. So now let's get started today's solution. We'll go through the detailed understanding of each and every options. And as so let's consider this series as an. Okay, so we have series an as n square into 2 raised to minus n. Okay, so I can write this one as n square upon 2 raised to n. Okay, take that denominator here, so we'll get the n square upon 2 raised to n. Okay, so here we can see our series, it's look like a series n running from 1 to infinity. So we can apply some of the conversion tests for the series. Okay, and one test is very much famous, that D'Albert's ratio test. Okay, so what is the D'Albert's ratio test? Say that D'Albert's, okay, so we have to apply here D'Albert's ratio test for finding the convergence of our series. Okay, so there are so many other options are there that you may apply for finding the convergence. Okay, there are some other tests also, but as I felt that D'Albert's ratio test is applicable here because of en is suitable for the D'Albert's ratio test. And D'Albert's ratio test, it says that when we have limit as n tends to infinity modulus of an plus 1 upon an. Okay, if we get the value for it is l. Okay, limit n tends to infinity n plus 1 upon n which is equal to l. Whenever if we get the l which is smaller than 1. Okay, if this l is smaller than 1, then that series is a convergent. Okay, l smaller than 1, then series convergent. Second, if l is bigger than 1, series divergent. Okay, always remember, if l is bigger than 1, series divergent, l is smaller than 1, series convergent. And if we get the l is equal to 1, then we say that test fail. Okay, that we cannot say it is convergent or divergent. Okay, so we have three conditions on our D'Albert's ratio test. Let's apply D'Albert's ratio test to our given series. Okay, so what we have here, we want the n plus 1 upon an. Okay, so if we have an as a n square upon 2 raised to n. Okay, this implies an plus 1 can be written as, okay, n plus 1 can be written as n plus 1 bracket square, n plus 1 bracket square upon 2 raised to n plus 1. Okay, just replace n by n plus 1, you will get the an plus 1. Okay, now substitute all these values over here. So limit as n tends to infinity modulus of an plus 1. Okay, that means n plus 1 bracket square and n plus 1 bracket square upon 2 raised to n plus 1. Okay, this is the value for an plus 1, and total completely divided by an. Okay, which is a n square upon 2 raised to n. Okay, and modulus complete. Now let's find out the value, what the value of our limit it gives us. Okay, so if one of the value it is coming here, so we can say divergent or convergent. Okay, now let's go for the next step. So take that numerator of numerator, this one is numerator, this one is denominator. Okay, so numerator divided by denominator, so denominator of denominator it comes numerator. So we write limit as n tends to infinity n plus 1 bracket square upon 2 raised to n plus 1. Okay, this is the numerator multiplied by denominator 2 raised to n upon n square. Okay, so what I have done, I just replace numerator by denominator. Okay, and I taken as a multiplicand. So 2 raised to n plus 1 can be written as 2 raised to n plus 1 written as 2 raised to n into 2 raised to 1. Okay, so this one cancel with this one. Okay, so we'll get the limit as n tends to infinity. Okay, so here left here 2 and n square. Numerator it comes a plus b square n plus 1 bracket square. Okay, a square plus twice of ab plus b square we have to apply over here. Okay, that means n square plus twice of n into 1 plus b square means 1. Okay, so a plus b expansion I used here. So as if we apply directly limit to the our function, it gives us the value infinity. Okay, and we do not want infinity over here. So try to remove that n square from denominator, take n square common from numerator and cancel it here. Okay, so we'll get the limit as n tends to infinity. Okay, n square common here, 1 plus 2 by n plus 1 by n square. Okay, when I take n common from the numerator, so n square multiplied by 2. Okay, this one get cancelled with this, so we have to apply the limit for the next step. Limit as n tends to infinity, so 1 upon 2 common here, under bracket 1 plus 2 by n plus 1 by n square. Okay, so 1 plus 2 by n, 2 by n, 2 upon infinity 0, 1 upon infinity 0 when we apply limit, so we left here with 1 by 2. Okay, now we can see here by applying D'Albert's ratio test, I got the answer for our series is 1 by 2, and which says that if L, that is 1 by 2, is smaller than 1, then we say that series is convergent. So here we got the 1 by 2 which is smaller than 1. So by using D'Albert's ratio test, we say that series is convergent. Okay, I hope you all have understood my first option. Just we have to apply D'Albert's ratio test in order to check whether series is convergent or not. Okay, now let's move for the option number B. We'll see what test is applicable there. So here in our option second, we can see that we have given option second n raised to minus 2 into 2 raised to n. So an can be written as 2 raised to n upon 2 raised to n power to the power n. Okay, 2 to the power n, and n raised to minus 2. So this is the value for an. Okay, and 2 raised to n upon n raised to minus 2. So here it is n raised to plus 2 it is coming. Okay, numerator minus 2, then it comes plus 2. So I got the an as 2 raised to n upon n raised to 2. Okay, so it's similar like our first option. Okay, so we can apply here D'Albert's ratio test again. So as we learn it into our first option, so we need the term for an and an plus 1. So in order to apply D'Albert's ratio test. Okay, so we do have already an. Now find out an plus 1. So 2 raised to n plus 1 upon n plus 1 bracket square. Okay, so 2 raised to n plus 1 bracket here and upon n square, that means n plus 1 bracket square. So I found here the an and n plus 1. Let's apply the D'Albert's ratio test as a limit n tends to infinity, modulus of an plus 1 upon an. Okay, so let's find out the value here. Limit n tends to infinity, n plus 1. Okay, so mod n plus 1 it is here, 2 raised to n plus 1 upon n plus 1 bracket square completely divided by an. Okay, so an it comes as a 2 raised to n upon n square, 2 raised to n upon n square. Okay, now replace denominator with the numerator, you will get the 2 multiplicand term here. So how we go through the next step? Limit as n tends to infinity. Okay, so numerator as it is 2 raised to n plus 1 upon n plus 1 bracket square. Okay, so multiplied by numerator of numerator, denominator of denominator, it always numerator, n square upon 2 raised to n. Okay, bracket complete. So 2 raised to n cancel with this one. Okay, so we'll get the limit as n tends to infinity under bracket. So 2 raised to n, 2 raised to n, which is get cancelled. Okay, and here we left 2 with the n square. Okay, so 2 times n square upon n plus 1 bracket square. Okay, that means a square plus twice of ab plus b square. Okay, so this is the expansion. So to cancel n square will get only the value similar like previous option. limit n tends to infinity under modulus 2 upon n square cancelled with n square, so 1 left. N square cancelled with n, so we get the 2 by n. N square cancelled with 1, so we get the 1 by n square. Okay, so apply limit n tends to infinity, so 2 by n, which is a 0, 2 upon infinity 0, 1 upon infinity 0, so limit n tends to infinity, this term it comes 1, so we'll get the value 2 only. Okay, and as we know that Dilbert's ratio test, which say that when L we get the smaller than 1, then and only then series convergent. Okay, but here we got the L is a 2, 2 is not smaller than 1, 2 is bigger than 1, so series is divergent. Okay, so by using Dilbert's ratio test, we can say easily here that our option number second series, which is a divergent. Okay, so it is very easy option. Now let's move for the third option. Now in our third option, we have given series n is equal to 2 to infinity 1 upon n log n. Why n is not equal to 1? But because log 1 it is not possible here. Okay, log 1 is given 0 and 1 upon 0 it goes to infinity. Okay, so for n is equal to 1, our series not defined. So we need a value from n is equal to 2 to infinity. Okay, so it seems like that we can apply Cauchy condensation test. Okay, which is very much important in real analysis for finding convergence or divergence. So we can apply here Cauchy condensation test for our convergence or divergence of a series. So by applying Cauchy condensation test, okay, by Cauchy condensation test, we can say that if series an decreasing sequence of a real number. Okay, so if we have sequence an which is a decreasing sequence of real number. Okay, so if we have condition sequence an is a decreasing sequence of positive real number. Okay, so sequence of positive real number, so we need a positive real number here. Then we say that series an, then we say that series an and series a2 raised to n into 2 raised to n behave alike. Okay, what these series do, these two series behave alike. Okay, that means the behavior for series an and the behavior of a series a2 raised to n and into 2 raised to n are alike, they are similar behave. Okay, when an is a decreasing sequence of a positive real number. Okay, so this condition is very much important. Okay, now here we can see if we apply n is equal to 2, 1 upon 2 log 2, 1 upon 3 log 3, 1 upon 4 log 4, all terms are coming positive. Okay, this condition hold because log 8 is defined here for all positive value. Okay, 1 upon 2 log 2, 3 log 3, all are positive, all are giving us a real value for value. Okay, all are giving us real values. So whenever any value you substitute here, 1 upon 2 log 2, it is belongs to real number. 1 upon 3 log 3 or upon 1 upon n log n, all goes to the real number. So or for the condition which is for Cauchy condensation test, it's satisfied over here. Okay, now we can apply series a to a series n and a to raised to n to raised to n. Okay, so that means if you wanted to find out the series n, so what we have an here, n we have here 1 upon n log n. Okay, that means the value for 1 upon n log n and the value for a2 raised to n into 2 raised to n. Okay, that means 1 upon 2 raised to n log 2 raised to n multiplied by 2 raised to n. Okay, that means how this term look like, 1 upon 2 raised to n log 2 raised to n. Okay, multiplied by 2 raised to n. So what I have done, I just replace n by this 2 raised to n and I multiplied 2 raised to n over here. So I got the an and this term, okay, over here, and these two terms behave alike. Okay, the behavior for this an and the behavior for this a2 raised to n 2 raised to n are similar. That means if this series is convergent, then this series is convergent. If this one is divergent, this one is divergent. Okay, now let's find out if this one is convergent or divergent. Okay, so for finding a2 raised to n 2 raised to n 2 raised to n 2 raised to n will be get cancelled. Okay, So it left here a2 raised to n into 2 raised to n as 1 upon log 2 raised to n, and by exponent rule you may take log n into the multiple. Okay, so 1 upon n multiplied by log of 2 raised to n. Okay, n it is not there, so n it is coming here. Okay, so by Cauchy condensation test I written here uh, 1 upon n log 2. Okay, so log 2 is a constant term. Okay, so if you multiply any constant term to 1 upon n, that doesn't matter. Okay, so we'll get the next step as 1 upon n. Okay, so I found here series. Okay, 1 upon n, so I converted 1 upon n log 1 n as a series 1 upon n. Okay, log 2 is a constant, so it doesn't affect to our series. Log 2 is a non-zero constant number, so it will give some positive valued number. Okay, so we do not need this one here, so we have to very careful about 1 upon n. Okay, and we have to check series 1 upon n is a convergent or divergent. Okay, and if you are familiar with the modulo p test, okay, so mod p test, it says that when we have series upon 1 upon n raised to p and p is strictly bigger than 1, okay, then series is convergent. Okay, when p is strictly bigger 1, then series is convergent, otherwise all value for series is divergent. Okay, so here we have p is equal to 1, which is smaller than 1. Okay, which is equal to 1, so it is not bigger than 1, so series is divergent. Okay, all value for p strictly bigger 1, series convergent, and all value for p smaller than 1, series is divergent. Okay, 1 or smaller than 1, so we have value 1 or smaller than 1, that means series is a divergent. Okay, and one more result is there that you may apply here for finding convergence or divergence. Okay, series 1 upon n log n raised to p, it is a convergent if p bigger strictly bigger 1, and divergent if p lesser equal 1. Okay, so you may apply this result over here for finding the solution. Okay, so option number C, which is a divergent over here. Okay, now let's move for the option number D. In our option number D, we have to find out whether this series is convergent or divergent. Okay, so a and we have here 1 upon n into log 1 plus 1 by n. Okay, so here we have to apply the expansion of a log of a plus b. Okay, so we have to apply log of a plus b, then we'll get the expanded form of this bracket. Okay, because we have to check whether log of 1 plus 1 by n convergent divergent. Okay, so let's find out the expansion over here, and then we'll figure it out whether n is convergent or divergent. So here in our option D, I written n here as n into log 1 plus 1 by n. Okay, so n as it is, I expanded log 1 plus 1 by n this way. Okay, the expansion of log 1 plus 1 by n, and here we can see, okay, n is a positive and monotonically decreasing. Okay, so n it is positive here, all the value for n which gives us a positive value. Okay, and whenever n goes bigger, denominator whole term goes smaller. Okay, so that means our n it is also decreasing series. When n tends to 0, then n into n it goes to 0. Okay, okay, when n tends to 0, then n into n it goes to 0 as n tends to infinity. Okay, so apply n tends to infinity, 1 upon infinity it will be go 0. Okay, so 1 upon infinity it will be 0 minus 1 upon infinity. Okay, this term it comes to multiple of 0, so 1 upon infinity it becomes 0. Okay, so if n tends to 0, n into n is a as n tends to infinity, then but n into n tends to infinity as n tends to infinity. So whenever we apply limit n tends to infinity to our an, okay, an which gives a non-zero value, and the standard result it says that if limit n tends to infinity, an which is non-zero, then series divergent. Okay, whenever you apply limit n tends to infinity to an, we'll get the n into n as n tends to infinity. Okay, that's why series an is a divergent over here. Okay, it is easy, very easy answer that you can answer it with the only observation. As a limit n tends to infinity an non-zero, then series an is divergent. Okay, now let us see the full solution for our question. So for your understanding, you may refer this solution of my question. Okay, which of the following is convergent? So the first option I explained over here. So here you can see the expansion. Okay, so option B I expanded over here. Okay, so solution option B here. So option C, I applied Cauchy condensation test and I shown A series an and A2 raised to n2 raised to n behave alike. Okay, So this is the complete solution, and if you wanted to see here, go for the option number D. Okay, so here option number D. Okay, you can see here, this is the complete solution for option D. Okay, I hope you all have understood my today's solution. It is a very easy question, completely based on convergence and divergence of the series. Okay, so very easy questions that even after, if you found anything difficult, let me know in comment section. I will come up with a similar video. So thank you everyone, thank you for my today's lecture.